empezar. Hoy esta mañana es crudo Cimat, Guanajuato, y empezamos por Javier. Para mí es un gustazo muy grande, digamos, presentar a Javier. Javier es todo el mundo conoce a Javier, entonces no voy a hablar de quién es Javier, pero es también una persona muy importante para mí. Y mi contacto con México es gracias a Javier. Entonces mis primeras estancias eran en Guanajuato, en Cimat, donde pasé mucho tiempo y aproveché mucho trabajando con Javier. Era sobre todo sobre el índice de campos electorales y pues siempre es muy bien, digamos, el lado científico, académico, pero también como persona, digamos, con su alegría, con su manera de ser. Es un gustazo trabajar con Javier y sus pláticas siempre son muy divertidas. Estoy seguro que va a ser lo mismo.
Muchas gracias, Pavao, por la introducción. I'd like to thank Professor Yuli Lyashenko for continuing his academic interest with Mexico. We appreciate very much all these 35 years we counted. We have had relations for 35 years, and thank you very much. Also, I would like to thank the organizing committees for inviting me, and I would like to congratulate Laura and Adolfo and the rest of the people that work in here in the Institute of Mathematics that have been forming this very nice group. So, as we have seen from Juli's lecture, we have some parameters, and then we have a dynamic space. So there are two spaces. There are the parameters. So these I'll draw like this. So these are the parameters. And then for every point in the parameter, we have in this thing that I'm going to speak about, so we have a copy of C2, and then the parameters will be A1 up to, and then B1 or B something, and to a point here, we're going to associate the vector field X equal, so this is the sum of Aij's, C1 to the I, C2 to the J, and then sum of Bij's, C1 to the I, C2 to the J. So here we have the parameter space, which are given by the coefficients of the polynomial vector field in C2. And then for every one of these, we have some picture. I tend to say that many people think mathematics are very boring because they think that mathematics is about the parameter space. So it's like the names of the object, but this is really the object. And so, so we have the parameters, and here we have the dynamic space. So in this dynamic space, what we will do is that we will solve the Newton equation. So this means that we are searching for solutions of this ordinary differential equation. And then here, if I put dc over dt with complex time. And so the object here, the solutions of the Newton equation associated to the vector field X, then will be a foliation by Riemann surfaces on C2 minus the set of points where x is equal to 0, where the vector field vanishes. And so I, and perhaps many of you would like to understand this picture. How is this foliation in C2 related with the coefficients? So when we move the coefficients, then the picture moves. The picture moves. Now, so this is the family I'm interested. I've been interested for a long time in understanding this picture. But I'm going to choose another family. See, this is one family, and we'll choose another family. So the other family, we have the same parameter space. So this time it will be these Aij's, Bij's, and a positive number. So if we call this parameter space here Cn times Cn, so these are the coefficients of the vector field. And so this will be in Cn cross Cn cross 0 infinity. So we have another extra parameter, and what we want to do is, so above over here, we will have the three-dimensional sphere. So we're going to raise the dimension by 1 instead of a two-dimensional sphere, three-dimensional sphere. And so, and the object associated to this, first there will be a vector field which is y equal to y times C1 x1 bar plus C2 x2 bar times x. So we're multiplying the vector field x by some complex number, which depends on the point and the vector field. And the interesting, so since we're multiplying by a function, the foliation defined is the same because it's the same complex vector field. Now, the problem with this function over here is the bars, because it takes us outside of our complex analysis course. And so this is a C-infinity function. But the merit of this function, of multiplying by this function, is that, so if we are going to S3R will be the points C1, C2 in such a way that the norm is R. So these are the spheres of radius R. And if we're giving a point over here, the x is a point, so defined by this. And what we're doing over here is that we have the tangent space, so this is a point P. We have the tangent space at P of the three-dimensional sphere of radius R, and we're going to multiply by a vector, by a constant, in such a way that, so we multiply this vector x at P with a complex number in such a way that we force it to be tangent to the spheres. And then, so the integrals, so the integrals of this equation, so we have dc, now we have real time equal to y. So the solutions of this function, of these differential equations, will be a function from R, and it goes the three-dimensional sphere to the three-dimensional sphere. So this is the dynamics on the three sphere generated by the vector field y. So we pushed every vector in such a way that it becomes tangent. And the assertion is that this simple function does that for you. And so the reason is very simple, is that if you take y and you take here the radial vector field, and you do the Hermitian inner product of the two, it's very easy to see that this is I, and then this is times, so this is the norm of, so let's call this guy over here, this is h. This is the function h. This is norm of IH squared. And the thing is that Hermitian inner product, the real part is the Euclidean inner product. So since this inner product is completely imaginary, this says that this vector field is tangent to all the spheres. And so we'll call y sub r, y restricted to the sphere. So we have this very complicated picture over there by Riemann surfaces. What we're doing is we're intersecting with the sphere and seeing what it looks like. And then this brings us to a simpler situation where we have a three-dimensional sphere. We have a real analytic vector field. Now, this real analytic vector field vanishes where H vanishes. So now, so this means that we have one of the things I'm going to say is that we're going to ask question for a generic parameter. So what this means is that there are going to be some open sets, where inside they represent the same topologically equivalent objects. And then when you pass from one set to the other set, then you have a bifurcation. So what we want to do is to associate a finite number of data that will characterize these stability sets. So instead, Yuli has been talking about the parameter space being all C-infinity vector fields, or all polynomial vector fields. Here, we are fixing the degree. So we're fixing the degree of the vector field with the coefficients, and then we have the radius. And I want to convince you that we may associate to a generic object a finite data, that this finite data characterizes the dynamics, and all vector fields that have the same data will be structurally stable in this family. So in doing this, we're choosing the family. So I will state a theorem we have been working on, and but we did some pictures that told us, because if I tell you what's the solution of this equation, I don't know. But the thing is that since this is a polynomial, we can feed it to the computer, and it will give us a simple answer. So here, the examples will be polynomials of degree 2. And what this picture says, I am going in reverse time. So these are initial conditions. I throw 10,000 initial conditions in the Riemann sphere. So the Riemann sphere, I take one point.
¿La 3 esfera o la?
Excuse me?
¿La 3 esfera?
¿Eh?
¿La 3 esfera?
La tres esfera. So this is on the three sphere. So what the pictures do is the following. You fix an R, you take the point at infinity out, so it's R3, and then you project into the screen. So we are seeing the projection, and so here I am doing reverse time. So what this means is that there is a repeller, and all the solutions are being bound in this repeller for this specific example. I'm doing how it looks for a specific example. Now, if I reverse the time, if I reverse time, let's see if I can get this working. Okay, so this is the same vector field, but I'm reversing time. I'm reversing time. I take it, the same 10,000 initial conditions, and I say flow with the equation of y sub r. And here, it turns out that for this specific example I made, there are two attractors. So this vector field has one hyperbolic repeller and two hyperbolic attractors. This already shows that this is very interesting, because if you have two attractors, you have to have a boundary between the two regions of attraction of each attractor. So there are some orbits that are not captured by the attractors. There are some orbits that have to belong to the separating set. So this means, the theorem, so this is a theorem I have with Manuel Cruz y Alfonso Cárdenas, and myself. So, for generic X and R, so this is a polynomial vector field of degree D restricted to a sphere of dimension R, we have, so one is a finite number of hyperbolic repellers. We have a finite number of hyperbolic attractors. Now, three. So for every alpha j and beta k, we have U of alpha j and beta k, which is an open set. So this is an open set in R3, which are born in alpha j and die in beta j. So we're going to have hyperbolic repellers, hyperbolic attractors, and these are the regions of attraction of the beta k and the region of repeller of the alpha j. So and these are disjunct open set. Now, we also have some set that we're going to call V sub L, which consist of periodic orbits. So this is an open set formed by periodic orbits with trivial holonomy. So this may look something like this. So here we have a couple of centers. So many of the pictures we have seen during the the lecture of Julie here will be repeated. So here we have, so this will be this open set formed by periodic orbits with trivial holonomy. And then 5, we have a separating set. Which is going to be formed. So this will be formed by, so I'm going to call them, I don't know how to write this in English, asymptotas, asymptotas that converge to saddles. So let me explain this. So, so the claim is that this is all that is happening for this. Now, these vector fields have the property that since they come from a holomorphic foliation, the holonomy maps are conformal maps. This means that the Poincaré maps, so I take an orbit, I take a transversal here, and I take another transversal here. And so the map which goes from initial conditions to final conditions will be a conformal map. This in particular has the implication that if I have a periodic orbit, then the first return map will be a conformal map. So its derivative will only have one eigenvalue. So either it's expanding, or it's contracting, or it has norm 1. But by this genericity hypothesis that I'm putting, I'm erasing the norm 1. So this means that the periodic orbits that we will have will be hyperbolic. The periodic orbits will be hyperbolic. Now, let me, let's say, the ones who are stealing the dynamics are these attractors and repellers. The union of this U alpha j beta k k will be an open set, and then we have this other open set which consists of periodic orbits, and we have the separating set, and that's all the dynamics there is. And in that sense, this finite information that we associate to each one of these will be how many attractors, how many repellers, what is the nature of the open set which goes from one repeller to one attractor. Then there are these bubbles of periodic orbits, and this union of all these form a dense open set on the sphere. And we have this separating set. So let me explain where does the separating set come from. So we're going to call sigma, if I not called it before. So sigma will be h equal to 0. Sigma r is h equal to 0 intersected with norm of z equal to r. So the first lemma is that for generic x and r, sigma is a surface and, excuse me?
What is h?
H is this function. H is the complex number you have to do to put it into the sphere. So where H vanishes, then the vector field vanishes, because I multiply by a function. So where H does not vanish, so X, I'm assuming I have a finite number of singular points, so I omit this finite number of singular points, And so the singular points of the vector field y are given by h equal to 0. Okay? Now, but then, so this sigma here, where h vanishes, is a surface, and this sigma r will be, so I call alpha, beta the attractors, so this will be gamma 1, gamma s. These are periodic orbits. I'm sorry, wait a minute. So these are, they're not orbits of the vector field, they are just S1 curves. So I have C2, I have the spheres, and then I have this surface over here. And so this surface will be intersecting the spheres in smooth, closed curves. So these are a finite number of, I'm fixing R. So these are S1 surfaces. And now on these S1 surfaces, there is a function A, which goes from sigma to R, A is equal to, so I take the determinant of the derivative of lambda times the identity minus the derivative of y at a restricted to sigma. I divide by t squared, and this gives me a function which goes from sigma to r. So what is this? So this is the characteristic polynomial of y at a singular point, because sigma are the singular points. But since sigma is a surface, I already know two eigenvalues are 0, the ones tangent to the surface. And so I can divide by t squared, canceling these two eigenvalues, and I'm left with the other two eigenvalues. Now, and then, so this will be something of the form then t squared plus a plus b t plus a. So this is the a. Where did I get the a? I got the a from the derivative of y and calculating the eigenvalues restricted to this set. And then I know there are two eigenvalues which are 0, so I get rid of them. And so this one here tells me what is the product of the two eigenvalues. So where a is positive, so if a is positive, then we have a center. If a is negative, we have a saddle. And so this means that the organizing information we need for the dynamics are the attractors, the repellers, and then we have one of these orbits, these gammas. They are the connected components of sigma intersected with the sphere. In one piece, we will have A positive. In another piece, we will have A negative. And then we have A positive and A negative. By genericity hypothesis, we're always passing from a positive to a negative through just one point. So at these points where it's positive, we have centers. And at these points, we have saddles. And so let me show you some pictures that got us to this conclusion. So here I was just showing the attraction and repeller. Okay. So let me explain this picture. See, this thing over here, these are the gammas. In black, you have the gammas, and then you can see you can see two components of these circles. So in this, they are centers. So here we have a small piece of a center. This is forming a bubble of the third kind, of the fourth kind, over here. And then in the other parts where of the critical set, in the other part of the critical set, we have the saddles. So the saddles are the ones which are going to be separating the sphere into these open sets. And so in this sense, it can happen that the saddle goes to an attractor. It can also happen that there's a saddle connection. We have saddle connections, and this, when we perturb in this family, this is stable. So we're not perturbing in an arbitrary family. This is not the space of C-infinity vector fields or real analytic vector fields. This is the family formed by polynomial vector fields of degree D intersecting with the sphere R. So let me show you more pictures. Instead of giving you the formal proof, let me show you some pictures which I think helped us get to this conclusion. Let me see. Now, here in this picture, what I want you to figure out, we're moving the coefficients. So this means we're moving here. We're moving here. So here we have this, and then what I'm painting here are only the attractors and the repeller. These first two pictures that I showed you was how do I get this red and blue. The blue are the attractors, and red is the repeller. And I'm moving the parameters. And so here we're watching the bifurcation, how the bifurcation comes. So what we want to understand is what are the pieces, and then what are the generic bifurcations. So when I go from one to the other, from one stable set to another stable set, now, of course, this is different. So that was this first one. Let me...
Javier, ¿los puntitos negros los recuerdas qué son?
Okay, let me... los puntitos negros. Let me... Okay, so the black points are these. The singular set. So the vector field is vanishing on a finite number of closed curves, which are not solutions to the vector field because they are singular points. And so when we're moving, you can see here how it's bifurcating. No? You can see, so it broke from one piece to two pieces.
So it is a discrete set?
Eh?
It is a discrete set, it's not connected. It's not that the computer doesn't connect.
So, okay, so let me tell you, to solve analytically this equation is hard. So the way we did this picture is the following. You take 10,000 points on the sphere. Now, you let the flow go. If the vector at the point on the flow is smaller than 0.0001, you make a point black at that point. So in this set, in this sense, I did not solve I did not solve the equation, but I used the vector field to let's see what this. let me erase everything. Por favor, Pava, ¿me dices cuando me faltan 5 minutos? Si no es que ya se acabaron mis 5 minutos. ¿Verdad? Okay. Let's see. Let's see this. So here we are seeing then, okay, so this was this picture where I showed you that these things over here, this VL, these periodic orbits with trivial holonomy, they do appear. So they are appearing over there. They are, so these come from centers which are located in this part of the singular set. And then when we move to the other part, then we have saddles. And then, so this picture I wrote over here actually can be completed because on the boundary of this set, we will have singular points, and so they will have to be saddles because we only have, see, due to this hypothesis that this AJ was either positive or negative, so these are circles, but then here we have, so saddle connection. We need to have saddle connections to embrace the parts with periodic orbits. So every segment formed by periodic orbits has to have on the boundary at least one segment formed by saddles. And so let me show you some other pictures. Are there any questions? Is this very confusing? 5 minutes, okay. So I'll show you the last picture. Oof. Okay, so I want to show you this picture. So I explained to you that we have one repeller and two attractors. So what we do is we put a torus, a small torus, around, let's say, the repeller, the same thing with the attractor. Now, the thing is that if you make reverse time, once you pass to the boundary of this torus, you know what's happening, because all the time you will be winding around this periodic orbit. So, and then over here you put another torus, and then you picture on the boundary of this torus, how does it look, the points which go to this one or go to this other one. Everybody except the separating set is being born in this torus, but part of them have to go to this one, and the other part have to go to this other one. And so, what we're doing in this picture that already passed, let me get rid of everything. No, doesn't work. Okay, so let me. 3 minutes. Okay, so here we do like this. No. We go here. We put this. Okay. We put this and we. Okay. Let me. Okay, so see, this is the torus we put around the repeller. And deep blue is the ones which go to one attractor, and the other blue, it goes to the other attractor. Now, in order to construct the dynamics, we have similar in the other torus. So we have a point here which begins here and then goes to this attractor. But then on the attractor we put a torus so it hits a specific point. So we get a map from part of the torus here to part of the torus here. And so the torus that we put around the attractors and the repellers and the partition that I put in this statement over here, they form part of this torus, and there is a map which connects the initial conditions to final condition, and this is capturing the dynamics in most of the space. The part of the space which is not captured is that we have this finite number of regions of periodic orbits, and we have this separating set. So this makes a simplified dynamics. Now, of course, if we call Z and we raise the I, then this is a vector field which is always pointing inside. And so we'd like to figure out how these dynamics that I explained on spheres, which is simple, gets mixed up with the other vector field to construct the original foliation that we're interested in doing. So in that thing, the vector field, the original vector field, we split it into two real vector fields. One of them turns out to be very simple because it's tangent to the spheres. And the other one, we hope to understand and then try to understand the picture in situ. Thank you very much.
In your drawings, the repellers and the attractors look like periodic orbits.
Excuse me?
In your drawings, the repellers and the attractors look like periodic orbits. What can you say about the repellers and the attractors in general?
Which one?
Anyone?
I'm sorry, what's this?
Yes.
So this we got from the, so the picture suggested to us that, let's say, if you compare to rational dynamics of one holomorphic function, then you have this Julia set and you have this Fatou set. So the Fatou sets, so here we have the attractors and the repellers. Now, to get the explicit form of them is impossible. We just figure out by the computer pictures that that's what was really happening. So the dynamics, since it's conformal dynamics, we don't have a Julia set kind of phenomenon. The Julia set becomes the separating set. So to get an explicit description, let's say our Hilbert 16 problem would be to find a bound on the number of attractors and the bound on the number of repellers and a bound on the number of components of this set and how much it changes sign in terms of the degree. So in that sense, these are questions which correspond, some finiteness things coming from the polynomial vector field. But your question is?
That when we throw a torus around the attractor, it suggests that the attractor is a periodic orbit. Oh, no.
Yeah, the attractor is a periodic orbit of the flow. So these are periodic orbits of the flow, which are hyperbolic repellers and hyperbolic attractors. Okay. These ones, and they are stealing the show because most of the things are born in one and end in the other. So you still have these bubbles, which I show you that they really appear, these ones, and then so these are the open sets which are born in one and die in the other. These are these bubbles, and then you have the separating set, and that's all.
Okay, so there are no strange attractors.
There are no strange attractors. So our original question here was, what's the Julia set? And so we figure out we didn't see any Julia set in any of the pictures. We didn't see any funny behavior. No, everything was very controlled. So it seems that the conformal dynamics controls the stuff. And then we had to So the computer gave us an idea of what the statement of the theorem should be. And then we had to do some complex analysis and complex dynamics to figure out that this is the theorem. And so the dynamics here is simple. Now we'd like to get to the other vector.
Other questions?
In your blue terms, there are two blues, so there is this curve separating the two regions. And it seems that when you're doing one twist along a tracker, there is a twist.
There's here, you're talking about this picture?
Yeah, this picture.
So this picture means that the set seems to be like a 1-1 curve,
Yeah.
because it's going around once and once. So to get the complete picture, one would have to say that this is contractible to a curve, and then to say what's the homology of the curve. So this would be part of the complete picture. The other thing is in some sense, who cares where it lies, if it is inside the attractor or the repeller? But that seems to be a difficult question, to determine what is the topology of this color set. That seems to be a difficult question. So here at least one would say it's non-empty. And then one would be satisfied. You have parts are born here, die over here, but you don't be precise to say what's the homology class of the open set, which seems to be a difficult question. A ver, permíteme. Jesús, ¿tú querías preguntar algo?
Are there some bounds between the number of repellers and the degree of the original vector field X?
Okay, so what we have, we don't have a complete bound, but the thing is the following. If the radius of the sphere becomes very big, then in the polynomial vector field, the leading terms will be the higher order terms. So if the higher order terms are sufficiently generic, then what happens in the homogeneous case will also happen for big spheres. So in that case, we have the bound. We have a bound for big spheres. But then when the spheres become smaller, then you have some other bifurcations. And we still don't understand what are the generic bifurcations that appear. That's one question that follows. So in principle, we don't have a bound. Actually, these alphas and betas, the only way we have of getting them is with the computer, because where are the attractors?
The point in your argument is that you consider the sphere really in a non-special point for X. Assume that the original X is hyperbolic, and then put the sphere in one of the spheres.
Yeah, of course. We began exactly with this case. So we put a hyperbolic singular point at 0, and so when the sphere is very small, what you see is two periodic orbits, one attractor and one repeller, and sigma is 0, doesn't exist. Then you start making the sphere bigger, and suddenly another attractor appears. And so for us it was good news, because if another attractor appears, it means that there has to be a boundary between the two attractors, so there has to be something that is doing something different. And so what is this? So this would be the Julia set. And so we traced where the Julia set came from, and the dynamics was only saddles, they're saddles. And then we discovered that also you had these bubbles of periodic orbits. So in that sense, the dynamics is very simple. We hope that this simplicity will help us to understand the flow in situ, the holomorphic flow.
So I think we should go to the next lecture.
Luego me pregunto.
Yes.
Bueno, muchas gracias.
Javier.